Welcome. Welcome. My name is Steve Miller. I'm a math professor at Williams College, and this is the second part of our lectures from Pascal's triangle to calculus. My son, who's going to help me go through this. And so what I want to do is I want to just quickly review what we did last time. So just to turn off the video here so it saves a little bit of power. Okay. So last time we saw what Pascal's triangle was, and we saw how to expand things out when multiplying. And one of the reasons we like Pascal's triangle is it helps us compute the coefficients when we expand things like x plus y squared or x plus y cubed. And so just moving forward, there's a lot of structure here. There's actually a fractal structure. We'll see a little bit more with fractals in a little bit. We then did a little bit of algebra and limits. So we talked about linear functions like 3x minus 5, 7x plus 2. These are functions that are to the first power in x. We talked about how to evaluate them by putting in a value for x and plotting them. We talked about plotting a quadratic. We talked about plotting even higher ones like a cubic degree 3. Then we talked about limits. And so we talked about the limit as x goes to 2. We've talked how to compute that. Well, if we're writing x going to 2, we can write x as 2 plus h and take the limit as h goes to 0. And we frequently do limits like this, and we try to remember that when we send h to 0, h is never 0, it's just getting really close. So we did a lot of computations of limits. So here's a great example of a limit, x squared minus 4 over x minus 2. So when we put in 2, we get 4 minus 4, which is 0, 2 minus 2, which is 0. But when we went out and did all the work, we thought that it was just equal to 2. Not all limits easy to find. We then went into a quick introduction to calculus and differentiation. So we talked about average speed. So if we start at home at time 0, and at time 2, we've traveled 110 miles, what's our average speed? That would just be 110, the total distance traveled, divided by 2, the amount of time, or 55 miles per hour would be the average speed. And so we can calculate average speed. We can look at it graphically. If this red line or red curve denotes where we are, then we're here at time A, we're here at time B. This is the change in distance, b minus f of a, the numerator, and this is the change in time, b minus a. And so that ratio will be the average speed. And so we calculated that the average speed for a linear function is constant. We calculated for a quadratic function, then it was a little bit more interesting. The average speed of x squared plus 3x plus 1 from a to b was b plus a over 3. And then if we took the limit as b goes to a, we would get 2a plus 3, and this would be the instantaneous speed. So if you want to think about how your car calculates speed, it's going to measure how far you've traveled in smaller and smaller amounts of time. And if it's a small enough amount of time, that average speed is a really good approximation to the instantaneous speed. And so we did a little plot, and we looked at trying to calculate the average speed from 1 to a little bit more than 1. And we saw as we got closer and closer to 1, these seem to be converging to about 5. But if we try to do the average speed from 1 to 1, then we're going to blow it up 0 over 0. Right. The other thing worth noting is that the straight line, that's pretty good, which is where we assume our speed is constant, does a pretty good job locally of approximating the function. So as you go further out, it's going to get worse and worse. So the instantaneous speed is the limit as h goes to 0 of this ratio, the change in distance over the change in time. Well, the denominator simplifies nicely to just h. And so we write this as f prime. We call this the derivative of f. It's a new function. And we like to write it like this because it reminds us of where it came from. So we then calculated the derivative of a linear function 3x plus 5. And we saw that was just 3. Where is the 3 coming from? It's coming from the 3 and 3x plus 5. More generally, if we took the linear function cx plus d, its derivative was just c, and that's coming from here. We then studied a quadratic function. We did the calculation. We used Pascal's triangle to expand x plus h squared. When we looked at f of x plus h minus f of x, we got the change in distance, that's the numerator. We divided by h. We got 6x plus 3h plus 5. And as h goes to 0, what does 6x go to?
6x.
6x. What does 3h go to as a
0.
plus? And what does 5 go to? So we get 6x plus 5. Yep, so we were here last time. I'm just doing a quick review. So how did we get this from the 3x squared plus 5x plus 2?
The 3 times the
Yes,
coefficient.
3 times the 2 was the 6, and the power of x goes down by 1.
Yeah, I remember
And so
that.
here, 5x to the 1, this 5 is 5 times 1, and the power of x has gone down by 1. So more generally, if we have ax squared plus bx plus c, the derivative is 2ax plus b.
Yeah.
And you correctly guessed that if we had a cubic, ax cubed plus bx squared plus cx plus d, it would be 3ax squared plus 2bx plus c. What if I gave you x to the 4? What do you think that would be?
4ax to the third.
4 to the third. And so what that's telling you is as x gets larger and larger and larger, is the speed getting going
Greater?
up?
Yeah.
Yeah, if you think about it, if your distance is x to the 4, at time 0 you're 0, at time 1 you're 1, at time 2 you're 2 to the 4th, which is
2 to the 4th, 16.
and at time 3 you're 3 to the 4th, which is
3, it's 27 times 3, right?
yep, or 9 times 9.
Oh, so 81.
81. And you can see that you're traveling.
That off the top of my head.
You're traveling much faster. So you go from the first moment of time, you traveled 1 unit from 0 to 1. The second moment, you traveled from 1 to 14, you traveled 15 units. The next moment, you traveled 81 minus 16,
Yeah.
which is what, 65?
That sounds about right.
So you're going much, much faster. So you can see that an answer like 4x cubed is reasonable. Your speed is getting faster and faster and faster. And so that's what we just said over here. The key ingredient to find this was Pascal's triangle. And so why do we care about all this? And so the reason is we can use the instantaneous speed to approximate the function. So if you take a complicated function, what we can do is we can do the point slope method. We have a point on the curve, we have the slope, the instantaneous speed, and we draw the straight line that goes through the curve at that point with that instantaneous speed. And that should be a really good approximation to the function.
Yes.
So for this function, here we had 3x squared plus 5x plus 2. So f prime is 6x plus 5. When x equals 2, f of 2, we just put in 2, we get 12 plus 10 plus 2 is 24. The speed is 17. So we have the point is 2, f of 2, or 224. The slope is 17. So we get y minus the y value, 24, is the slope 17, x minus 2. Or we can simplify it to y equals 17x minus 10. And then are we surprised? No, because if you don't have time change that much, your speed should still be pretty close to the 17.
Yeah.
All right, so now in the last part of the lecture, this is the new stuff. This is divide and conquer versus Newton's method. And we're going to see some fractals and chaos and some wonderful applications of calculus. So much of math is about solving equations. So if I give you ax plus b equals 0, it's not too bad to solve that. We subtract b from both sides and we divide by a.
Yeah.
Now, I don't think you've done this yet in school, how you'd solve a quadratic. But it turns out that there's a way to do this, and there's a nice formula, that the roots are negative b plus or minus the square root of b squared minus 4ac over 2a. What's nice is you can use the method of divine inspiration. If someone tells you these are the roots, you can plug them in and see if it makes this expression 0. And then how do you find them? That's a topic of another lecture. It turns out that if I give you a degree 3 function or a degree 4 function, there are solutions for the roots in terms of the coefficients in closed form, but this is not the case for degree 5 and higher. There is no general solution, but there are ways to estimate. Now, is negative b over a, is that hard to evaluate?
Negative b over a?
Yeah.
No.
No. Over here, negative b plus minus square root of b squared minus 4ac over 2a. It's a little bit worse, but is it terrible?
Not really.
Not really. Here is one of the solutions.
That looks easy.
These are the solutions for the cubic. And they involve I, which is the square root of negative 1. So you can see the I over here. Here's
What is the square root of negative 1?
So it's not a real number, because I times I is negative 1, and no real number times a real number is negative. So here's just one of the solutions for the quartic.
So what's like this square root of, say, like -5.
So the square root of -5 would be I times the square root of 5.
So it'd be I times 5?
I times the square root of 5.
Okay.
So it'd be like,
So if it was, so the square root of 4 would be I times 2?
well, the square root of 4 is just
-4, I mean. The square root of
would just be 2I and -2I. So those aren't too bad to find. But we're actually going to try to find square roots now. So let's talk about the divide and conquer method. Assume we have a continuous function. So continuous function means I can draw it without any breaks on the paper. This is not like Star Trek where you have a transporter and 1 second you're on the Enterprise and the next second you're on the ground. Do you know why they have transporters in Star Trek?
Because it's easier.
Well, they didn't have enough budget for when the series first came out to have a shuttle leaving the Enterprise and going to the planet. So they said, well, what if we just press a button? We don't have to build the set, and now all of a sudden you're on the planet. Done. Sold. So imagine we have a...
It's funny, like, everybody talks about that. It's just like it's a cheap option.
Cheap, but hey, cheap options often good. Now, imagine we have a continuous function, so there's no breaks as I draw. It starts off negative over here, and it ends positive at 1. What must happen between 0 and 1?
It becomes positive.
It becomes positive. So in particular, what must happen?
It crosses the x-axis.
So if it crosses the x-axis, that means there must be a root, there must be a place where the function is 0.
Yep.
We're trying to find roots. We're trying to solve f of x equals 0.
It's kind of be hard for it not to be.
Right. And so this is just writing it in more math speed. So assume our function is continuous. That means it has no breaks. It's negative at a. It's positive at b. Then f has a root between a and b. And to find it, we can look at the sign of f at the midpoint. If the sign is positive, so if the function is positive here, then the root has to be between 0 and here. If it's negative, it has to be between the midpoint and 1. It's possible the function could have many roots. It could go up, down, up. That's fine. We know there has to be at least one root. And then what we do is we do the shampoo method of mathematics. Lather, rinse, repeat. We just keep looking at small and small intervals. So for example, imagine f of 0 is negative and f of 1 is positive. So we look at the midpoint, f of a half. And let's say f of a half is 2. So it goes negative, positive, positive. Must there be a root between 0 and a half?
Yeah.
Must there be a root between a half and 1?
Yeah.
Between a half and 1.
Wait.
So at a half it's 2, and at 1 it's 3.
No.
No, it could stay positive all the way there, but we know because it's negative at 0 and it's positive at a half, that there must be at least one root. So let's try a quarter. And now let's assume that at a quarter it's equal to negative 0.4.
Then no.
So now we know it's negative at 0 and negative at a quarter.
I mean, it could be.
It could be.
It could go like.
Right, but it doesn't have to be.
Yeah.
What about it's negative at a quarter and it's positive at a half?
Negative at a quarter, positive at a half.
So must there be a root between?
Yes.
Yes. And so we look at 3/8, and we can keep playing this game. So it's also, it works, it's easy to do. We just need to tell if the function is positive or negative, but it's slow. So here's 10 iterations trying to find the square root of 3. So the square root of 3 is about 1.732. So we know
Does
that
that go on to, is that like pi in a way? Like it just keeps going?
It keeps going on and on and on. It does not repeat.
Yeah.
Because if it repeated, it would be rational.
Yeah.
So here's the thing. We know that the root is 1 squared is 1, 2 squared is 4. So the square root of 3 is between 1 and 2. So if we try 1 and 2, we look at the function x squared minus 3. When we put in 1, we get negative 2. When we put in 2, we get 1. Does there have to be a sign change now? Went from negative to positive. Yes. So we know that there's a 0 somewhere between these two. If we look at 1.5, we see f of 1.5 is negative 0.75, which is negative. F of 2 is 1, which is positive. Is there a sign change between these two?
Wait, yes.
Yes. So we now look between 1.5 and 1.75. And we see it goes from negative to positive, so there's a sign change.
There's a sign change between all of them.
Right, and so what I've done here is I've always done the correct one. So after 10 times, We know it's somewhere between 1.7304 and 1.732. The actual answer is 1.73205. So we're off by a little bit, but not terribly. So here's the question. How quickly does this work? Well, do you agree that every time we do this, we half the interval we're looking at?
Yes.
We start off first with the interval 1 to 2, which is of size 1, then 1/2 to 2, which is of size 1/2, then, well, I'm sorry, 1.5 to 2, then 1.5 to 1 3/4, which is a size 1/4. So every time we do it 10 times, we're going to have a factor of 1/2 to the 10.
What is 2 to the 10?
It's 1024. But here's the thing. 1024
So 24 is 2 to the 11.
is 2 to the 11.
Never knew that.
Is 1024 is approximately 1,000. So what this means is if we do this 10 times, the error goes down by a factor of 1/2 to the 10, 1/1024. That's approximately 1,000. So what this is telling us is every 10 iterations, we basically gain another 3 decimal digits. And if you look, we do have about 3 decimal digits. Almost. It's somewhere between 1.730 and 1.732. If we wanted to get 6 digits, we'd have to do this 20 times. If you wanted to get 9 digits, how many times?
30.
If you wanted to get 12 digits,
12. 40.
40. So it's slow. So I'm going to show you Newton's method now, which is fast. So earlier, we spent some time learning calculus. We learned about instantaneous speed. So assume that our function is continuous and differentiable, so we can find these instantaneous speeds. We can generate a sequence of numbers that will hopefully converge to the root. And what we're going to do is, given our guess xn, we're going to generate the next guess in the sequence xn plus 1 by looking at, here's our guess, xn. F of xn is the value of the function at that point. F prime of xn is the instantaneous speed. So we do our point slope form for the line. We see where it hits the x-axis. When it hits the x-axis, what's the value of y?
When it hits the x-axis, what do you
when the line hits the x-axis,
0.
0. So when we put in y equals 0, the value of x that makes y equals 0, we'll call that xn plus 1, our next guess. And when we do a little bit of algebra, we get the following formula. So let's see this in play. So here's the function, basically, x squared minus 3 equals 0. So we're trying to find the square root of 3.
Yeah.
And here's our first guess. We're going to guess 2. And here's the value of the function at 2. So since it's not 0, it means our guess wasn't right. So we draw the best straight line. We draw the straight line going through that point, the right instantaneous speed. And does this do a good job approximating the function for small amounts of time?
Yes.
So what we're going to say is, let's just pretend it's always the same as the function and see where that line hits the x-axis. And that's going to be our new guess x1. Is that perfectly right?
Yeah.
So then come up here, we'll draw the best fit line again with the instantaneous slope, and we'll keep playing. So let's do it slow. So we'll say we have x squared minus 3. That's our function. So what are the roots? When does x squared minus 3 equal 0? For what value of x?
When x is the square root of 3.
Good. Anything else?
The square root of negative 3.
Not the square root of negative 3, but the square root of 3.
And then this negative.
And then negative
Square root of 3.
Negative square root of 3. So if we square root, if we had the negative sign inside the square root, it would be wrong. But if we have it outside, when we square, the negative sign goes away. So we can write these down as the answer. But what are these numbers? We've just named them. We want to calculate them.
So we get a calculator.
Well, but how does the calculator find them? And that's what we're going to learn. So we're going to initially guess that 2 is the square root of 3.
Why 2?
I wanted something that was easy to work with, but not a tremendously good number, not a tremendously good guess, so you can't accuse me of stacking the deck. We agree that 2 is not a really good approximation.
Because let me know that 2 squared
is 4.
Yeah.
It's not a great guess. It's not terrible. So if we plug in x equals 2, what do we get if we plug in x equals 2?
Oh, so what is it? So 4 minus 3 is 1.
So we get 1. So this is not 0, so we have not found the root. What is f prime of x? So if we have f of x is x squared minus 3, do you remember how to calculate its derivative?
If you tell me, I don't remember.
Let's see if you can remember. What did you do? What's the derivative of x squared?
Square root of x.
No. How do you take the derivative of x to a
I
power?
forgot. Multiply by, oh, inside the FOIL?
No, that's expanding things. How would you take the derivative?
What's the derivative again?
That was the instantaneous speed. So when we went to like x squared, what was its derivative? You know,
X.
what do we do with the power? What do we do with the coefficient?
Oh, you moved it down by 1.
So we moved the power down by 1
and multiply the coefficient
and multiply
by
the coefficient by the power.
power. Yeah.
So what should the derivative of x squared be?
X. No, 2x.
2x. And the constant term goes away, and so we just, oops, there should not be a minus 3 there. That is a typo. We'll have to fix that. There should not be a minus 3. The derivative is just f prime of x is just 2x. And so what is the instantaneous speed at x equals 2? So again, the minus 3 shouldn't be here. What do we get when we put in 2?
When x equals 2,
Yeah,
4.
we get 4. So now we can find the tangent line. So we know the point is 2f of 2 or 2 comma 1. We know the slope is 4. So how would you do the equation for the line knowing a point on the slope? How would you write it? It is
2 is equal, right?
well, it's y,
Fine. Y equals mx plus 3.
but we don't know what b is. We know the
Fine.
point and the slope.
Okay, fine.
So do you remember the point slope form?
Yes.
Okay.
It's y equals mx plus b is the point slope form, right?
Nope.
So
That's slope intercept.
Okay, fine. So we need to find b.
Right. Or we can do right. But we can directly
There's
do.
a point-to-point thingy.
We
don't have
well, we could find another point. We could increase x by 1, and then no y would go up. But so one way to do it is it's y minus the y value equals the slope x minus the x value. This is the point slope form.
Yeah.
So we subtract y minus 1, and that equals 4 times x minus 2.
Yeah.
So if we bring this over to the other side, we get y equals 4x minus 7.
Mm-hmm.
So what value of x will have this hit the x-axis?
What value of x will have this at the x-axis?
Yeah, so if this is hitting the x-axis, what's the value of y?
0.
0. So when does 4x minus 7 equal 0?
4x minus 7?
Yes.
When 4x equals 7.
Okay, and when does 4x equal 7?
When x times 4 is 7.
And what is that? X equals?
Would it be the...
So if 4 times x equals 7. Solve for x.
The square root of the square
No,
root?
can't count.
Wait.
4 times x equals 7. What should you do to both sides?
Divide by 4.
And so x equals?
7 4.
So you would get x equals 7 4, so about 1.75. Right?
Yeah, that makes
So if you have 4x equals 7, x equals 7 4, that's not too bad. That's not a terrible guess.
sense. Yeah.
If you have 1.75, the answer is 1.732. So now let's do it again. So our new guess is x1 equals 7 fourths. And now we're going to find the new tangent line. So the point is going to be 7 fourths f of 7 fourths. So we put in 7 fourths here. What's 7 fourths squared?
Wouldn't it be just 7 fourths times 7 fourths? So do you multiply across?
Well, what's 7 fourths times 7 fourths? You multiply the two tops and you multiply the two bottoms.
So I was right. So 49/16.
So we have 49/16 minus 3. 16 times 3 is 48. So when you subtract, this is just going to be 1/16.
Okay.
And we said that the derivative is just 2x. So what's 2 times 7 fourths?
2 times 7 fourths.
Mm-hmm.
That would be 14/8, right?
We have 2 times 7 fourths.
Yeah, so 2 7 fourths, right?
Okay. So what's 7 fourths times 2?
What is that? So if 2 could also be like 2 over 2. Oh wait, no.
No, it's not.
No, it's 2 over 1.
It's 2 over 1.
Right, I was thinking of
Yeah.
1. That it would be 14/4. No, right? Yeah.
We have 2 times 7. It's right, so it's 14/4. And what's 14/4 the same as?
Something and a half. So 3.5.
So 4,
Yeah, 3.5.
3.5, or just 7/2.
Sure.
But since we had 14/4, if you're multiplying by 2, you can just change the 4 to a 2. So our point is 7/4, 1/16. The slope is 7/2. Is this close to 0, 1/16?
Is it close to 1/16?
Is 1/16 close to 0?
Yeah.
So we're actually pretty close now to a root. We're going to get a much closer. So now we want to find the best fit line again. So we have y minus the y coordinate, 1/16, equals the slope, 7/2, times x minus 7/4.
Yeah.
And so I've drawn the line in red now. And that's going to be the new point, x2. So what's the value of y when this line hits the x-axis?
0.
So we get 0. So we get negative 1/16 is 7/2 x minus 49.
Yeah.
How would you solve this? What would you do first?
Simplify that fraction. Right. Yeah.
So the fractions are all reduced.
Yeah.
So what's the first thing we should do?
Divide by 16. Right? I mean, multiply by 16.
So we could multiply by 16 to clear things. What else could we do? So let's.
Do that. Right. Oh.
So we have 7/2 x minus 49/8 equals negative 1/16.
Well, multiply both sides, everything by 2, so to get rid of the.
Or we could multiply by 16 to clear things a little bit more. But I'm saying, how could you simplify? What should you move from side to side?
The negative 49/8.
Yeah, move the negative 49/8 over here, so we have only x on one side.
Yeah.
And then what would we do?
So we move that, then we would multiply by 2.
Right, or multiply by 2/7 to get rid of these.
Sure.
So we could get 7/2 x is 97/16. We multiply by 2/7 and we get 97/56.
Then we have the first.
We have 1.73214 versus 1.73205. So we're off by 0.00009, basically.
Yeah.
Not bad. Okay, so we can keep going.
Until we like.
And
Well, technically, wouldn't we like never get there?
So we would
because
never
we'd have
get
to
there.
to infinity.
Correct. But we should get very, very close. So if we look at this, if you do a little bit of algebra, which would be a really good exercise, you get the next term in your guess is 1/2 your previous guess plus 3 divided by your previous guess.
Yeah.
So that's what happens if you simplify the algebra. Whenever you have a formula, you always want to test and see, is it reasonable? What would be the luckiest value for you to choose for your guess for the square root of 3?
The square root of 3.
The square root of 3. So let's see what would happen if we put that in. What's 3 divided by the square root of 3?
0. Wait, 3 divided by the square root of 3.
Yeah.
3 over the square root of 3.
Right, how would that simplify?
Well, that would sort of be like dividing like 4 by 2, right?
Yeah. What's 4 divided by 2?
2.
What's 100 divided by 10?
So it'd just be the square root of 3.
It would just be the square root of 3. And so what's the square root of 3 plus the square root of 3?
3?
Nope.
Oh, no. 2.
2 square roots of 3.
Yeah.
And then when we multiply by a half, we get?
The square root of 3.
So if we happen to choose the square root of 3, the next guess is also the square root of 3. So once we hit the square root of 3, we stay there. So here is looking at the first couple of choices. We did 9756, that was the second guess. The third guess becomes 18,817 over 10,864. They're always right. And look, we get 1.732050810. The correct answer is 1.732050807. So instead of 07, we're not off by that much. If you look at the fourth and the fifth one, so here's the fifth guess. Look at how far down you have to go before you see a difference. This is only with 5 guesses.
That seems accurate.
It is extremely accurate. And look, not only is it accurate, but we actually have it as a rational number. We'll always get a rational number.
Yeah.
Every time you do Newton's method, every time you do another guess, it basically doubles the number of decimal digits. So with divide and conquer, if we want 3 digits, that's 10. If we wanted 6 digits, it's 20. If we wanted 9 digits, it's
30.
Whereas here, every time we do it, we double the number of digits. So if we were to do it one more time, we got what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have over 30 digits now. We'd have over 60 digits, really, if we did it one more time.
So are we going to do it one more time?
Nah, I thought that was enough times. So we're going to end with a game.
Yeah, I like this.
So here's the game. Consider x squared minus 1. So we've seen this polynomial many times. We can write it as x minus 1 times x plus 1 equals 0. So if this equals 0, do you agree that either the first factor is 0 or the second factor is 0?
Yeah.
When does x minus 1 equal 0? What value of x?
1.
And when does x plus 1 equal 0?
-1.
So here are the two roots, 1 and -1. And so here's our formula to find the next guess. And so I'll color the 1 blue and the -1 red. And so the question is, if we start at a point, do we approach a root? And if so, which root? So if I started here, which root do you think we'll approach as we keep iterating?
The 1.
The 1. If I started here, which root?
-1.
-1. What if I start here? Less than 0, -1. What if I start here?
I mean, not -1, just 1.
Just 1. What if I start at exactly 0?
0. Both?
So can I be going to both?
No.
Or
You'd just be at 0.
maybe I just stay at 0. And in fact, if we tried our guess with 0, we would have 0 plus 1 over 0. Are we allowed to do 1 over 0?
Really, no.
So it's good that the method blows up and says, don't even try to do me at 0. And if you actually do Newton's method, it colors it exactly as you would expect. Everything that's positive goes to 1. Everything that's negative goes to -1. It is exactly what you would like to have happen.
That's nice.
Now we're going to do things a little bit more complicated. So we're going to look at x cubed minus 1 equals 0. So we're going to have to use complex numbers. I know you haven't really seen this stuff, but this is now using numbers of the form x plus I of y, where I is the square root of -1. And what you can do is you can view this graphically. So each point has a real part, which is the x-axis, and an imaginary part, which is the y-axis. So there are now 3 roots, and I'll color them, I think, blue, red, and green. If I start off over here, which root do you think I'm going to go to?
The blue?
The blue one. If I start off over here,
Red, green.
What if I start off over here?
Blue?
So how are you determining which root you go to?
I don't know.
Give me a simple rule. It may not be right.
Whichever one's closest?
Whichever one's closest. So how would you divide the plane so that you can find which root is closest to each point?
Find the halfway mark.
Yeah, find the halfway mark. So look, where's the halfway mark between these two?
Let's go like there, there, there.
And so here it is. So this will divide the plane into 3 regions. And so you would expect everything in here goes to red, everything here goes to green, everything here goes to blue.
But that's not right.
It is not right. And this is where the fractal shape comes into play. And so what's absurd is if you're near the root 1, then yes. But as you get near the border, amazingly, this point over here actually goes to green, while this point over here, which is almost the same as that, would go to red, and this point over here would go to blue. And so I'm going to try and hope that the internet works, because I'm going to go to the video.
No, it's not video.
It's this video right here.
What would you do without me?
And so hopefully it will now start to zoom in.
What do you have on me?
Yeah. And so what you can see is we're zooming in on the middle, and you can see this incredible self-similarity. This is what we saw when we looked at Pascal's triangle with the dots, where the numbers even or odd. And as you zoom in, you see this incredible, amazing behavior. And you see this extreme sensitivity to initial conditions. It's more than I can do in a quick talk here. So what I'm going to do now is I'm going to start this one. I'm going to set this one up.
Oh, I think I've seen this one before, right?
Oh. So I want to quickly go back to slides. And so I'm not really going to go into the Mandelbrot set, but this is the most famous fractal.
Why?
That would be a different lecture. And if we zoom in over here, and we can do that lecture later, we get this part over here. Then we zoom in on this part, and we get this part over here. And then we zoom in on this part, and we get this part over here. And so I'm not going to play the cheesy music, but a lot of times I will play it, but it often has issues when I. So we'll see if it records well. And so this is doing a zoom. And so we're zooming in at this point over here. And what the colors indicate is how quickly you go to infinity, you iterate, or stay bounded.
Don't we see it again?
And so we will see it again.
What?
So it's taking a while, we're zooming in. This is a 5-minute video. And again, the scale at which we're going in is incredible. And it's not easy to calculate something this well. So in a later lecture, we will actually talk about how we can do these calculations. Because colors being off by just a little bit will lead to very different behavior. So we should be getting into another Mandelbrot set soon. And there you can see it. There is another copy of the set. And zooming in again. And again, tremendously difficult to do these calculations. The whole point of all this is that small changes in initial conditions can lead to wildly different behavior. So zooming, 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 zooming.
I've already seen this before.
Yeah. Well, that's one of the main things is that it has this incredible. So it looks like we should be getting close to it again.
We just faster. We just faster.
Okay.
We'll stick.
Still zooming, still zooming, still zooming. Still zooming. I haven't seen the Mandelbrot set again, but kind of pretty pictures.
There.
There it is. And so this is only about halfway with all the zooms. And so, I'm shooting all the way towards the end of the video. We'll see if the internet is good enough to allow us to play the very end of the video. I'm not sure if the video will resume because unfortunately the Wi-Fi is not so good anymore here.
It was never true. Oh.
And so you can see a little bit over here just by holding it over there. So I'm going to stop the share. I will go back to slides. And then basically just there's a bunch of links you can go to. And again, why do we care about all this? We care because small changes can lead to wildly different behavior. And this shows us we have to be careful when we have to solve problems in the real world. So again, this was a quick introduction to calculus and to some of the applications. And so the video, again, let's just stop that. I'll go back and finish up. So the big thing we saw here was that we used calculus to find lines that approximated our function. And rather than dealing with our function, which was complicated, we instead were able to deal with these straight lines. And do you know how to find equations for straight lines?
Yeah.
Yeah, you learned that in Algebra 1. If I give you the slope and the intercept, is that your favorite y? Yeah, because it's just y equals mx plus b. So if I give you slope intercept, it's kind of easy. But you know what? If I give you the point and the slope, it's not so bad. So here's the point, 7/4 f of 7/4. Here's the slope, f prime of 7/4. And so I can just plug that in here. That's not a big deal. If I want to find when does this equal 0, I just take y equals 0. So we can do this without too much trouble.
Yeah.
So this is a really nice application of calculus, because we can approximate complicated functions with simple functions. And in your algebra class, you're spending all of this time on lines. To some extent, if you understand lines, you understand everything. You can build things up in terms of lines. So I hope you enjoyed today's lecture. Have a great day.